Hello, my name is Porathe, and I am Professor of Interaction Design from NTNU, the Norwegian University of Science and Technology. I will talk about human factors, autonomous ships, and constrained coastal navigation. And contributing to this paper is also Kai Fjørtoft from Sintef Ocean and Ingelill Brattbergshagen from Kongsberg Seatex, and we are all from Trondheim in Norway. On the picture, you see the hull of Gjøra Birkeland, what could be one of the first commercial autonomous merchant vessels that has recently arrived in Norway for outfitting, although the pandemic has presently holding up the project. The title says Constrained Navigation, because in the Munin project some 5 years ago, we conceptualized open ocean navigation, which is relatively simple, with few navigational hazards and few encounters with other ships. What we now are attempting will be much more complex. Constrained navigation on national Norwegian waters in narrow archipelagos with relatively heavy traffic and summertime an abundance of leisure crafts. But most of all, this presentation will be about human factors. Human factors in two senses. One, I will try and present the concept of operation in a non-technical way that is easy to understand. And two, I will focus on the human in the autonomous ship system. I think that most of us by now have realized that for a foreseeable future, the human will play a key role also for unmanned ships. They will do that in many respects, but I will here focus on their roles as operators, monitoring and sometimes controlling mass from a remote operations center, a ROC. As we today do not have any ROCs, the image here shows an operator in a VTS center, a job with some similarities to what we will be talking about soon. But we do have some concepts, and here is a visionary illustration from the Rolls-Royce division working with MASS, now incorporated in Kongsberg Maritime. We see the human operator in front of a lot of sophisticated screens, lots of information. So let's stop here for a minute and remind ourselves of some human factors that limits our abilities. Humans have some limitation compared to machines. For instance, we get tired and must sleep. We do not work optimally during night as humans are day animals. We also have a limited attention span. This is a complex issue, but most researchers agree that humans cannot work with focused attention more than, say, 10 to 20 minutes at a time. Humans also have a limited working memory. This limits our ability to perceive information to a relatively small number of chunks, as George Miller famously stated in a 1956 paper, 7 plus minus 2 chunks of information. To help her survive, humans has developed what Freud called defense mechanisms. One such is normality bias, the opposite of denial. When things go wrong, many of us tend to deny that anything bad is happening and confirm signs that everything is normal. And finally, in this selection of examples, if we have not paid attention for some time and an alarm calls on us, it will take us some time to get into the loop, the so-called out of the loop syndrome. During this time, automation will have to cope by itself. So how do we then build remote operation centers that obey human limitations? Here, for instance, is another vision of what a remote operator station might look like. The Gjøra Birkeland control room in Oslo as it was presented at Norrköping last year. But still, lots of information. Or here, which is a concept drawing of the operator station for Autoferry, the autonomous harbor ferry in Trondheim. Still, lots of information. In the Moonin project, we tried to minimize the information for an operator that was monitoring 6 ships on an open ocean voyage to basically a green circle saying that the ship was on track and on course and that all systems were go. Here, on the final demonstration at Fraunhofer Center for Maritime Logistics in Hamburg in 2015. A big difference when it comes to operator workload is that between active and passive monitoring. We can assume that for many years to come, we will need to have active monitoring. IMO and flag states will most certainly demand that the operators are paying attention and are ready to intervene whenever something goes wrong. In the Moonin project, we were actually designing for active monitoring. The procedure was that the operator, who was monitoring 6 different ships on the open ocean, should spend 10 minutes every hour on board every ship, actively looking at some predefined key indicators, such as ship performance, course speed, roll, heave, slamming, etc., environment, potential traffic conflicts, fishing boats, and so on. However, humans are notoriously bad monitors. Once mass systems has matured and technology works well with few interventions, the risk is that active monitoring will quickly slip into passive monitoring. A maritime accident investigation branch investigator recently talked about boredom-induced accident. And an abundance of research shows that humans are not good at monitoring well-functioning automation. There is a reference at the bottom of this slide if anyone wants to study this further. So how do we then tackle these limitations to human abilities? One way is planning for optimal operator workload. On this image, we see a mass that is planned to go from A to B. The first and last part of the voyage, we can foresee high workload due to constrained navigation and heavy traffic. We could conclude that an operator cannot oversee more than maybe 1 ship. However, during the middle phase of the voyage, no traffic is expected, so an operator will have a low workload and can maybe oversee several ships. By scheduling operators with an alternating workload, we provide better working conditions. Based on such a planning, operators can be scheduled with different operator readiness levels. This will be beneficial from a human factors point of view. For instance, the operator is not tied to the operator station all the time and can be available on call during parts of his workday. In the Moonin project, we assumed a simplistic HMI paradigm, where information was available as needed but not visible when everything was working okay. The design was centered around the green circle, the top flag, indicating that all was okay. But there was also tools to drill down into every aspect of the ship and its navigation. So, let's conduct a Norwegian coastal voyage according to this. The time is 12:58. Our ship is about to depart, and the operator is at her station in readiness level red, in control. She is waiting for the green flag. 2 minutes to departure. If she is impatient, she can click on the red circle and see the flags underneath and see how they become green and what is presently holding the departure up. Aha, the linesmen are not yet in position. For this ship there is not yet an automatic docking system. In the meantime, the operator clicks on the flag saying operational status, which opens a screen showing the life expectancy of the combined ship system. In this screenshot from the Moonin project, We are preparing for a voyage from London, Gravesend, to Orinoco in Venezuela, a voyage of 240 hours, with a possible repair stop at Gran Canarias, 135 hours away. We can see that the combined system has an expected lifetime with full redundancy of 380 hours. Clicking on the bar leads us to the next level, and we can in this way drill down into all individual systems of the ship and get a prognosis for the expected lifetime. Easier said than done, but maybe good vision. In the meantime, the linesman has sent the ready signal and the top lamp turns green. All systems are go. The operator can start the voyage by clicking the play button. But before she does that, she just wants to check the pier side to see that everything is okay. She turns on the port side camera. She doesn't need to, but she's curious and maybe does not quite trust the system yet. She also turns on the starboard side camera to check if there is any kayaks on the outside of the vessel. Everything looks fine. She switches on the chart view and clicks the play button and watches as the ship leaves the pier. The voyage has started and the timeline appears at the bottom of the screen with the planned operator readiness levels indicated. The green top flag have now an indicator showing the ship in track following mode. The operator readiness level is now yellow, medium, indicating that the operator has a maximum response time of 15 minutes. She can now go and grab a cup of coffee. And as soon as the ship is out on open water, the operator readiness level changes to green, low. The operator is now on call on her cell phone with a maximum response time of 1 hour. But while she is away drinking her coffee, we will stay and watch as the mode indicator changes from track following mode to automatic control. The sensor system has detected a stand-on vessel from starboard and the automatic control units plans an evasive maneuver to give way for the ship according to cool regs. Here, a human observer may wonder what the automation is planning to do. Can I be sure that the automation is to be trusted? Now we come to the interesting field of automation transparency, or explainable AI, as the artificial intelligence people call it. How can the operator in a rock know what the automation, the AI, is thinking? And how can bridge officers on other ships know what the autonomous vessel plans to do? This is about communication between humans and here we see a simple concept illustration of how automation transparency could look for a trivial situation. At the bottom of the screen, you see the autonomous vessel, the own ship, on a northerly course. In the top right corner comes the stand-on vessel. She's called Lisboa. The screen shows the automatic controller's intention to turn starboard and pass behind Lisboa along the solid green line. This is a cool reg compliant maneuver and the automation gives it some confidence index of 98. The controller also lists some other possible lines of action with dashed lines and lower confidence levels. Should the operator have a different opinion, she could at any time click an alternative action and thus override the controller. Or she can just simply grab the joystick and take manual control. Well, it might not just be as simple as that. But this will be a very interesting area for future research. how the operator cooperates with the automation. And as the ship proceeds on its voyage alone, we will go back to our research, and we hope to be back on the next conference with some more results. Thank you very much for listening.